Okay. Good afternoon, everyone. Welcome. Today's colloquium is a Ph.D. defense. It's my pleasure to introduce today's colloquium speaker and Ph.D. candidate, Zoë Brooke Zibton of Viroqua, Wisconsin. I've known Zoe since what I believe was our first undergraduate advising meeting at 3:30 on the 26th of August in 2015. Although I learned today that April has a special significance to her in this department. Her first time in this room was on April 19th of 2013 when Professor Martin invited her as a visiting student to his 100 class to Weather Watch on Friday, April 13th. So it's an interesting connection here. She earned her Ph.D. in AOS as well as a certificate in environmental studies in 2017. And last spring she completed her Ph.D. minor in the Delta program with her certificate. Zoe's service to our department is notable in its breadth, organization, inclusiveness, and effective implementation, while also maintaining progress toward the completion of her Ph.D. dissertation. Zoe's service has contributed immensely to the building of community within our department through her organizing graduation celebrations, conceiving of and helping implement the AOS mentoring program for undergraduates, AMP, her work on graduate student recruiting, the colloquia and seminar organizing, as well as a participant in our recently activated DEI activities. And this list goes on. What doesn't she do? She also, some things that you might not know about Zoe, she's a ballroom dancer, choreographer, as well as a forecaster. I have just a quick slides to share. This is 5 years ago, 3 days ago this is at the honors senior honors thesis ceremony, receiving a certificate after presentation. This is the spring senior on the roof, end of semester party. This was in May 3rd of 2017. So she's up there making a weird face. I don't understand that quite frankly. But then after she was assimilated by the Borg in Portugal at an adjoint seminar, she began to evolve. This is her also in Portugal. And into quite a scholar. This is a presentation she was giving in, I think it was not Houston, it was Austin, Texas. And also she's a forecaster. She's forecasted for some of the CrossFit games here in Madison over the summer. But really, it's my delight, pleasure to introduce her and turn it over for her talk today, which is Adjoint sensitivity studies of tropical cyclone intensity measures. So thanks, Zoe, for giving this presentation, and I hope you have fun with it.
Alrighty, thank you for that introduction. Is this a good volume? Too loud, too quiet? Too weird hearing an echo? All right. So, good afternoon. As Michael said, today I'll present a subset of my PhD dissertation titled Adjoint Sensitivity of Tropical Cyclone Intensity Measures. Within the title itself, there's a lot to unpack, so we're going to go through the different elements in the title. First, talking about adjoint sensitivities. Next, going into tropical cyclones, and specifically tropical cyclone intensity measures, and wrapping it up with a general case study approach that we'll be using. Adjoint sensitivities. What are they? Adjoint sensitivity studies involve the evaluation of how a specific function, called the response function, of model output changes with respect to changes in the model initial conditions. Given these sensitivity gradients defined mathematically as dr dx naught, one can compute changes to the response function attributed to small changes in the initial conditions. This mathematically is defined as a dot product of the sensitivity gradients with the perturbed initial conditions. To perform an adjoint sensitivity experiment, the nonlinear model, or forecast model as you may know it, integrates forward the model state vector x naught to a model forecast state time xf. At this final time, the response function is defined, which is some aspect in the forecast we're interested in evaluating. In this case, we're interested in TC intensity metrics. At the final time, we use this response function to initiate the adjoint model. The adjoint is defined as a transpose of the tangent linear approximation to the fully nonlinear model. The tangent linear model is a linearized version of the fully nonlinear model, and it propagates forward perturbed conditions. The adjoint model itself is initiated with the gradient of the response function and integrated backward in time in order to recover information about how that response function, defined at the final time, is sensitive to our model state conditions. An example of this we'll go through is from a published study of Doyle et al. 2012, which goes through the case study of tropical cyclogenesis. Here is the model domain, and within this box is the response function domain. Shown in the fill is the magnitude of wind at 850 hectopascals and its wind vectors. In this case study, they defined the response function as the kinetic energy, as shown up here, with the goal of increasing the kinetic energy at this final time. They used the gradient of this to initiate the adjoint backward in time 18 hours, at which point they got sensitivity gradients. Panel A is showing the the control domain field of zonal winds and wind vectors at 850 hectopascals. Panel B is the sensitivity to zonal wind, and D is the sensitivity to water vapor. How we interpret this, if I were to add a positive perturbation to a positive sensitivity, we'd expect an increase in that response function 18 hours later. So in the zonal wind, if we increase the westerlies to the south of this C, the cyclone center, and increase the easterlies to the north of the cyclone center, we'd expect a more intense cyclone as measured by kinetic energy 18 hours later. Additionally, if we increase the moisture in an annulus around the TC at this time, 18 hours later, we'd expect a more intense cyclone as measured by kinetic energy, shown up here. Before I move on, are there any questions? A lot. Feel free to ask as we go through also. So now, what are tropical cyclones? Here is showing a cross-section through a well-developed TC. Panel A is the storm relative wind. Panel B is the perturbed temperature relative to the ambient environment. And panel C is the equivalent potential temperature, or beta E. So tropical cyclones are localized vortices of elevated cyclonic vorticity, as shown in panel A, with a strong circulation in the lower troposphere that decays radially with large radial gradients of the decrease in wind. Additionally, as we go vertically, the strength of the cyclone decreases consistent with thermal wind balances such that in the upper troposphere, an anticyclone develops. Due to this anticyclone in the center of the TC called the eye, we see subsidence associated with this warm core structure in the temperature. In the eye walls, as denoted by these yellow arrows, we see high equivalent potential temperature. Same warm and moist air is located here that goes from the surface up into the outflow layers, as shown by the expanding of the arrows. This radial wind, positive cyclonic vorticity near the surface, is considered its primary circulation, and its secondary circulation is considered an overturning circulation that's typically associated with the Carnot heat cycle. This cycle is first really described as a representation of a TC in a manual in 1986, related to the TC's maximum potential intensity. There are 4 legs in the Carnot cycle. Today I'm really concerned with leg 1 and 2, the inward inflow near the surface layer and the upward and outward expansion within the eye wall. While there are various different ways we can define intensities within a TC, I'm most concerned about how can TC intensity be quantified and measured within the context of an adjoint study. And how do we appropriately define a response function to measure TC intensity? So the National Hurricane Center defines TC intensity by the surface maximum wind speeds of the storm. There is some debate between the relationship between the maximum wind speed and the minimum inceptual pressure and the utility of relating these variables. Additionally, Some people consider the TC intensity as the magnitude of the cyclonic circulation, the region outside the inner core, so the primary circulation, as well as the strength of the overturning thermal circulation, or secondary circulation. It's important to ask ourselves, what is the relationship between these different metrics for TC intensity? Also, are there other metrics that are not as directly linked to wind, such as rainfall or storm surge, that could better capture how strong a storm is? And how does that relate to the use of TC intensity in, say, landfalling hurricanes? Furthermore, very important question is how are these intensity measures represented in a model so that we can use them to define our response function in an adjoint study? Recalling response function is, here are 3 typical response functions within an adjoint case study. Selecting the response function is our initial step in this adjoint studies and requires careful consideration in order to make sure that we're measuring the correct aspect of the forecast that we're intending to. In addition to making sure the variable we're evaluating is correct, we also want to make sure that the relative size of the response function is appropriate, such that if there's a slight track shift, we aren't missing the value we're intending to measure. 3 traditionally used response functions for adjoint intensity metrics are surface pressure. Within the WRF model, we use negative mu prime, where mu is the dry perturbation air mass within a column. It's a proxy for sea level pressure. The negative is there such that a positive sensitivity corresponds to an increase in intensity. The vertical vorticity is essentially measuring the cyclonic circulation around the core associated with that primary circulation. In today's talk, we won't talk about that. Kinetic energy, as shown in the Doyle study earlier, is another typical measure for intensity within adjoint response function, where increasing the kinetic energy is associated with increasing the magnitude of the winds within your response function. There's a caveat, though, to this kinetic energy response function, as there's 2 different ways you can really increase the kinetic energy. Here's a simple model to explain that point. The red box in all of these is denoting a response function domain. The black are sea level pressure contours. Pink and blue are the positive and negative cyclonic, or positive and negative relative vorticity, and the barbs are wind vectors. So one way to increase this control cyclone, or one way to increase the kinetic energy within this response function domain would be to deepen the cyclone, thereby increasing that pressure gradient and building up the kinetic energy while also increasing the cyclone's intensity. Alternatively, we could shift the cyclone center outside of the response function domain while building up a ridge nearby, still increasing the magnitude of that gradient and increasing the kinetic energy. However, if we're interested in understanding the dynamics that are leading to tropical cyclone intensity change, this does not tell us that, and thus kinetic energy as a response function can lead to misleading results. Because of that, we developed a new response function called vortex-associated kinetic energy, or VAK. VAK is calculated by taking the model state U and V wind, calculating the relative vorticity, and then separating that into the TC and the environmental relative vorticity. We then take the relative vorticity of the TC and through invertibility principles recover the U and V winds just associated with that cyclonic vorticity of the TC. We use those winds to then calculate our response function, VAK. In order to initiate our adjoint model, however, we need the sensitivity of the response function to the model state variables. Therefore, we take the adjoint of this above process to recover the sensitivity to the response function VAK to U and V winds. Going back to this simple example, it's hypothesized that VAK will perform more optimally because it focuses on changing the perturbations in the center of the response function domain. consistent with the idea of the superposition principle, where the greatest overlap of perturbation stream function and perturbation relative vorticity leads to the largest change in the perturbation kinetic energy. It's expected as these perturbations to evolve, they contract about the TC center, therefore resulting in a higher linearity due to less of a shift in the position of the TC, which is a major source of nonlinearity. This was developed as a kind of a complementary response function to a steering flow response function developed by Hoover and Morgan in 2011. The last part of this title is studies. So how are we going to use these different aspects of adjoint sensitivities and tropical cyclones and intensity measures to evaluate cases? Something important to note is within the literature, there are very few studies of using adjoint sensitivity methods on TC intensity. Some of the few is Ito et al. In 2011, where on a very short time scale, a 1 hour simulation at a high resolution within a axisymmetric non-hydrostatic model, they found that both stronger near-surface wind friction and a reduction in moist air supply in the exterior region of the TC can serve to strengthen the tangential velocity, which was the response function. Chu et al. Used the WRF, which is a 3-dimensional model, 4-dimensional model, a full model that found low-level moisture exerts a strong influence on the final time forecasted intensity. Doyle et al. In 2012, in a tropical cyclogenesis case, found that low-level moisture and temperature perturbations were of greater importance than winds on the intensity. They also found that these low-level sensitivities grew upward, suggesting a bottom-up development process occurred. Similarly, He, 2018, found intensity is more sensitive to increasing the primary over the secondary circulation of the TC. Additionally, increasing the temperature and moisture within the eye wall was of importance. Similar to Doyle et al. 2012, they found perturbations showed a bottom-up development. Lastly, while not a TC study, Doyle et al. 2019 evaluated a case study of an extratropical high-impact weather event using multiple response functions and found a juxtaposition and overlap of these different sensitivities, further emphasizing the response function definition and how it influences our sensitivities. Given all that background information and previous studies, we'll then get into the meat of the questions we'll be asking today. The context of how we'll approach these questions is a case study approach using adjoint-derived sensitivities for each case. They are calculated. We then calculate optimal perturbations to elicit prescribed change in the TC intensity. And finally, we evaluate the differences between the control and the perturbed simulation and its linearity as to evaluate the impact. The research questions that guided this research are, first, what process allows small perturbations to the initial earlier state to modulate future TC intensity? How do sensitivities of TC measures change based on the definition of adjoint response functions? And finally, how does the simulated TC intensity respond to partitioned adjoint-informed perturbations? Starting with research question 1, part of this is also to just see if we can replicate some of the previous studies that have been done. As referenced a number of times, we also include optimal perturbations, where optimal perturbations are initial condition perturbations with a minimum energy as defined by this energy norm. These optimal perturbations produce a prescribed change, shown down here, where the initial condition perturbations are added to the control simulation in order to perturb the nonlinear model. It's important also to evaluate the linearity of how these perturbations are evolved, as we are using an adjoint model which has a linear assumption in it. So we do this by evaluating the evolved change compared to the prescribed change shown mathematically here, We take the ratio of those change, which I'll call the linearity ratio, which calculates how well that linear assumption is held, with 1 meaning they evolve perfectly linear, and any deviations from 1 is a source of linearity, lack of linearity. Linearity fails in a lot of moist processes, also when track changes occur. Additionally, as you're configuring your model and simulation length, how high a resolution can influence whether or not linearity can be held. We'll first evaluate a case study of Hurricane Florence in 2018 with the WRF version 3.8.1 and its adjoint, doing an 18-kilometer resolution simulation with 41 evenly spaced vertical levels initiated with GFS data for a 36-hour model integration forward and backward. The model domain is shown here with the response function domain in red. This is showing sea level pressure in gray and mu in black. We'll be using mu, which is the dry surface pressure response function for this case study. We're doing a quick synoptic evolution. Here's the mid-level, low-level relative humidity in fill, and the sea level pressure in contours, the 200 to 850 hectopascal shear, and the 200 hectopascal potential vorticity in the fill, and the magnitude of the wind at 200 hectopascals in blue. As this simulation evolves, we see generally favorable conditions for development, sufficiently moist, low-level environment, low to moderate vertical wind shear, and we see that the outflow is developing as indicated by negative and lowering potential vorticity expanding out from the TC center. We also see an outflow jet starting to develop. At this final time is when we define a response function, where R, again, is surface pressure, and our objective is to calculate, describe, and interpret adjoint sensitivities. And here is our, excuse me, our response function domain within that red box. The adjoint sensitivities at the initial time are shown here. This is one representative variable, sensitivity to water vapor at 850 hectopascals. Note the strongly positive annulus of water sensitivity to water vapor around the TC core, saying if I make it moister, now the response function mu that we define 36 hours later would be stronger. In addition to the strong annulus about the TC, we see this strong maxima in positive sensitivity to the west. This is coincident with a minimum in relative vorticity, which is indicating a physical connection between these sensitivities and the synoptic state, such as if we were to increase the moisture in this area, we potentially see less effects by downdrafts and dry air entrainment as this simulation progresses. In addition to looking at horizontal distribution of these sensitivities, we'll take a snapshot of the vertical distribution. This is showing the fraction of sensitivity per level, essentially telling us where is the dominant signal. And all these sensitivities, shown as the zonal, the meridional sensitivity, the sensitivity to potential temperature, and the sensitivity to water vapor, and the according colors. We see a maximum in the boundary layer and near the surface that decrease vertically with a secondary local maxima in the outflow 300 to 200 hectopascal range. This is consistent with previous studies. We then say we want to prescribe a change, which in this case is a 1 hectopascal average increase in negative mu within the response function domain, so decrease the sea level pressure. In order to make this prescribed change, we again use this energy norm to constrain that change. We can also look at this distribution of perturbation energies to see how does those change vary vertically, noting that this is not the actual energy quantity, just a proportional change of these variables that I'm showing. So that's what we see here. Again, noting the similarity between sensitivities and perturbations at this initial time, which is what we'd expect. We can then compare that to 36 hours later at the final time, where the perturbation energy for kinetic energy and available potential energy are greatest in the upper troposphere. The perturbation latent heat energy maximized in the lower troposphere. This is consistent with the bottom-up process that previous studies have found. This upward development, shown here, prompted the question of what contribution do these upper tropospheric sensitivities that are very small have in developing the TC, and conversely, if we don't include those upper perturbations, can the bottom lower troposphere perturbations evolve and create this change on their own? To analyze this, we made the same prescribed change to just the upper level sensitivities and just the lower level sensitivities. This comes to our third research question of how does the simulated TC intensity respond to partitioned, adjoint, and growing perturbations? So again, this is our full perturbation experiment here, and we prescribed this change across just the upper perturbations and the lower perturbations, resulting in 3 separate experiments. The model levels separating upper and lower are defined here. We're calling that because the sensitivities are so much smaller in the upper troposphere. In order to get the same prescribed change, we have to make a larger magnitude change in these winds and temperature, et cetera, and moisture. So the magnitude of these upper perturbations is 13.1 times that in the full perturbation experiment, and 0 below 220 model levels. That's indicated again in the dashed line, dotted line. Dashed line is the lower perturbation experiment, which has a very similar structure to what we saw in the full perturbation experiment, because that's where the largest concentration of perturbations are to begin with. As we allow those perturbations in the 3 different experiments to evolve, we see a remarkably similar distribution of the perturbations from all 3 experiments, indicating how closely tied to developing that specific response function of dry surface pressure these perturbations are evolving to change. One notable difference is the fraction of perturbed energy for the upper perturbation is slightly larger in the upper troposphere compared to the full and lower perturbation experiment.
Can I ask a question quick?
Yeah.
So when you're perturbing either the temperature or the moisture, do you check to see whether you are creating regions of supersaturation? Is there any consideration taken for that?
I haven't explicitly calculated that. I have looked at, since the sensitivities are the greatest in the lower troposphere, I've looked at the changes in relative humidity at the initial time, and it actually decreased, so I don't think that's the case. Also, I've done a calculation of the prescribed change between potential temperature and water vapor doesn't change that much compared to temperature, so we're increasing the temperature a lot while not increasing the water vapor as much, so that isn't, I don't think, a concern in this case. So this is the vertical energy perturbation structure, what's actually happening to the response function. The contours and fills are the same variables across them for the upper perturbation, lower perturbation, and full perturbation experiments, where the black contour is the control simulation, mu, the perturbed mu in the nonlinear model is purple, and the change in the response function defined as negative mu perturbed minus negative mu control is in the fill. Notably, positive in a positive change is associated with an increase in intensity. Signs are a little weird. Anywho, we see pretty stark differences between the upper perturbation experiment and the lower and full perturbation experiment. Where the upper perturbation experiment, the magnitude of the change is significantly larger. It also has a shift to the west compared to a smaller change in the lower and full perturbation experiment that shifts southward. We can also look at the linearity ratio to see how does the prescribed change we made evolve. We see that the linearity ratio in the upper perturbation experiment is nearly 1, so it evolved very linearly compared to the lower perturbation experiment, which really didn't obtain any linearity to it, and the full perturbation, which also has a pretty low linearity ratio. Our question then is, why is this the case? What's causing the variations in this linearity ratio? To do this, we can look at the evolution of the tangent linear model of perturbations, which is now shown in green. The background is the same fill pattern as before. Before comparing the tangent linear and the nonlinear model, note that there's additionally a shift in the tangent linear model, which was not entirely expected, that a shift in location would result in an increase in intensity. We also see that the magnitude of change is the largest, substantially so, same contour interval, or the upper perturbation experiment, then the lower and the full perturbation experiment, saying that both the nonlinear model and the tangent linear model, when prescribed the same change, the upper perturbation experiment is evolving a larger change. And we want to understand why is this the case. So going back and looking at some different variables, here's the azimuthally averaged azimuthal wind, so essentially showing the primary circulation. This is at the initial time through the full, lower, and upper perturbation. At the initial time, we don't see much change differences. I'll also note for the people in the back, that screen is going to show a significantly more elucidating picture. The projection kind of messes up some of it. But at the initial time, we don't see much organization to it. At hour 3, we do start seeing some actual changes emerge. Notably, something that we can't see with this projector is in the upper troposphere, where an anticyclone starts developing in the upper perturbation experiment, we start to see a decrease in the azimuthal wind, or an increase in the anticyclone, which I promise you is there. We don't see that same change in the full or lower perturbation experiment. As the simulation steps forward, we continue to see changes, the largest changes occurring in the upper perturbation experiment. At the final time, we see a much more robust anticyclone developing in the upper perturbation experiment. We also see it shifting slightly inward. We also see a strengthening of the cyclonic circulation farther up, and also a reorientation of some of the extent of the vertical azimuthal flow. We again see this decrease in all 3 simulations. That's pretty coincident, saying to increase the anticyclone a little bit closer to the core, but the signal is a lot more muted in the full and lower perturbation experiment. We can also do this analysis with the azimuthally averaged radial wind, where negative indicates inflow and positive is outflow in the control simulation, which is in these contours. Time 0, again, no real structure is evident. At time 3, so 3 hours into the integration, we start to see some patterns emerging. Particularly, it's evident without adding arrows in the upper perturbation experiment. We're starting to see a more intense outflow. Also a change in the orientation or decrease in this contour. Something that you can't see in the lower and full perturbation experiment is where there's this increase in the outflow. In the upper perturbation experiment, we actually see a reduction in the radial outflow, suggesting not only is the upper perturbation experiment developing an outflow circulation earlier on and more robustly, that we're not getting that same signature in when we're just perturbing the lower perturbation or full perturbation experiment, suggesting that the importance of developing the outflow. Again, we can't allow this to go forward. The perturbations are always larger in the upper perturbation experiment. At this final time, we see a pretty similar structure overall between the 3 simulations. However, the magnitude is the greatest in the upper perturbation experiment, lowering and increasing the outward flow and the outflow. You actually see a reduction in the outflow or little change in the full and lower perturbation experiment. This is telling us a physical link of why are we seeing a greater linearity and a greater development of the sea level pressure in the upper perturbation experiment. We can also take a look at this from the view of potential vorticity. So this is the 200 hectopascal potential vorticity, that upper perturbation experiment at time 0 and time 36. The perturbation experiment is in fill, and this blue contour is the control simulation 0 PBU line, just for reference to see expansion. Even at the initial time, we're starting to see a few more arrows of lower and negative potential vorticity, which is associated with a more robust outflow, and at the final time, we continue to see that expansion. And comparing it to the full and lower perturbation experiment at the final time, we see that it's broader in this upper perturbation experiment. So we're seeing some outflow driving development.
And those means, what are those values?
Oh, yes. So within this box shown is the maximum and minimum value between the perturbed and the control simulation. So how far from 0, and also the mean is the difference between control and perturbed simulation. Where we see the upper perturbation has decreased about an order of magnitude larger or 2 compared to the lower and full perturbation experiment. Going to make those numbers bigger, just in case you can't see it visually. So summarizing from our research question 1 and 2, similar to previous studies, we saw the largest initial condition sensitivities are in the lower troposphere. In this case, we saw they're predominantly to potential temperature and wind, and less so to water vapor. Extra calculation is not shown. When we partitioned these optimal perturbations, we found all of them resulted in an increase in TC intensity and a shift in the track. However, the full and lower perturbation experiments did not evolve as much or as linearly. They also evolved very similarly because of how they were calculated. The upper perturbation experiment, on the other hand, evolved and resulted in a change that was comparable to what was prescribed, and we notably saw that this change seems to be driven by the outflow developing earlier. Another thing we noted is that the tangent linear perturbations revealed a shift in their location that was also different from the nonlinear model. This then brings us to considering how we're defining a response function and allowing that shift to occur within the response function domain. We don't specify how we're wanting to change the surface pressure within that domain, just that we want to decrease it. This brings us to our second research question of how do sensitivities of TC intensity measures change based on the definition of adjoint response functions. We'll now look at a case of Hurricane Irma in 2017, when it was again undergoing rapid intensification using a WRF at 18-kilometer grid spacing, now with 65 evenly spaced vertical levels. This is only a 24-hour integration over this model domain. The response functions horizontal extent, again shown in red. I could have mentioned this earlier. It's a 20 by 20 grid spaces centered on level 6 of the maximum and relative vorticity. And when applicable, we're using vertical levels from 6 to 10 within the model domain, so we're just outside the boundary layer. The fill patterns are the same as what I showed in Florence for relative humidity, vertical shear, and potential vorticity. Again, we see generally favorable synoptic conditions for development, higher relative humidity in the lower troposphere, in this case more moderate vertical wind shear. We also see a very robust outflow from earlier on that's developing outflow jets. An important thing to note at this final time is there's a broad lower tropospheric anticyclone to the northeast adjacent to the TC. This sets up adequate conditions to test kinetic energy versus vake. Here's our response function domain again, and our response functions we're using are comparing kinetic energy, vake, vortex-associated kinetic energy, and dry surface pressure. This is a column integrated value for kinetic energy and vake to just show distribution with the 1,000 hectopascal sea level pressure contour on there for reference. So we use the gradient of each of these three response functions in order to initiate the adjoint 3 times to compare sensitivities and eventually compare perturbations based on those sensitivities. The initial time, we can look at the sensitivity to potential temperature at 200 hectopascals. Broadly, we see a lot of similarities across the 3 response functions, but there are distinct differences. Within this circle, we see broadly consistent positive sensitivity to the northwest of the TC, indicating how closely related the kinetic energy, Vake, and mu response functions are. However, we do see notable differences in the sensitivity patterns. For instance, to the south of the TC, kinetic energy says to cool the air. Vake has a mixed pattern, and mu has a increase the potential temperature. This indicates if we were to make a perturbation in the same region across the 3 response function domains, we'd see varying increase or decrease in intensity depending on how we define our response function. We can also look at derived variables. This is the 850 hectopascal sensitivity to relative vorticity. This can give us a little bit more information than looking at the U and V winds separately. Note that here we see increasingly different sensitivity patterns with almost a reversal of the positive and negative sensitivity to vorticity between Vake and kinetic energy, and then mu is doing its own thing in the larger model environment. Zooming in just to kind of the near environment, we do see this similarity in the center of the TC, indicating making it more positively cyclonic, with an inward spiral of positive and negative sensitivities. This links back to an OR mechanism where bands of positive and negative sensitivities can lead to vortex growth. Similar to the Florence case, we can look at the vertical distribution of sensitivities. Again, finding the strongest sensitivities are in the lower troposphere. Note in this case, there's a few extra lines indicated by the Vake, kinetic energy, and U response functions, and solid, dashed, and dotted, respectively. The colors are the same. However, in this case, I'm only perturbing the U and V winds, so I've muted the potential temperature and water vapor sensitivities. In this case, the prescribed changes are a little bit different across each of them because they're not the same response function. So kinetic energy and Vake response function, I increased by 5% of the average of the control sum of Vake, just so I can compare apples to apples of how much energy I'm putting into the system. And then for the prescribed change in mu is 0.25 hectopascals, average increase in negative mu within the response function domain. This again, doing a back of the envelope calculation, resulted in the same initial perturbed kinetic energy, or very close to it. Again, use this energy norm to constrain our perturbations, and we can look at the vertical distribution of these perturbations with, again, Vake and solid, KE and dashed, and the dotted is a mu experiment. We see kinetic energy has the largest dependence on near surface perturbations to winds. In the mid-troposphere, we see a slightly larger dependence on perturbed kinetic energy in the KE and mu response functions. So the time 0, 24 hours later, as that response function evolved, again, we see this bottom-up process where the largest perturbation energy is in the upper troposphere for KE and EPE. We also see a remarkably similar distribution linking back to how closely related these 3 intensity metrics that we're using are. Now to compare the actual response functions, the first column is kinetic energy. Similar to before, the fill pattern is the perturbed minus control. Perturbed nonlinear variable for kinetic energy is in purple, and the control kinetic energy is in black. Here we're seeing an increase in this gradient of kinetic energy and a shift to the southwest. Again, the same control, perturb and fill as in kinetic energy, but now with the Bake variable. Here we're seeing mostly a broadening and a shift to the west, more centered within this response function domain. And lastly, looking at the difference in minus mu, we see again a shift mostly to the west and a deepening of the average mu. We take a look at the linearity ratios. Vague linearity performs most optimally with a 0.24 linearity ratio, followed by mu, and lastly kinetic energy. So the vague response function is adhering best to our linear assumption. All of them are not super high though. So let's evaluate where some of these linearity is lost. The same fill pattern for each KE, Bake, and mu. Now the tangent linear perturbations are on top of them. Particularly with the Bake response function, we're seeing a pretty high overlap of positive and negative regions between the nonlinear model difference and the tangent linear model perturbations, saying the structure of the perturbations that evolve is highly related. However, the magnitude of the change is different, so that's a large contribution of where we're losing linearity in the nonlinear model. We see a pretty similar situation with KE response function where magnitude is the largest decrease in linearity, but there's also some reversal in signs. That's a little bit more evident. Similar to in the Florence case, we see a reversal of the tangent linear model and the nonlinear model orientation of perturbations, again indicating there's no structure associated with where we're trying to decrease the pressure within this response function domain. We can also look at other derived variables. This is the string function, perturbed string function recovered from the perturbed vorticity. We see in the Bake response function that we're really decreasing psi in the center of the domain with a small shift. The kinetic energy response function, we see more of a shift to the southwest, building up that anticyclone. So this is suggesting part of the issue of why we're not seeing an intensity change in the kinetic energy response function is just the shift and possibly tapping into the anticyclone. And then mu, the change is mostly associated with this shift. We can also look at average values within the response function domain to just see average change that occurred. Red is the largest magnitude of change for that respective variable, and green is the smallest magnitude change. Big takeaway from here, within the response function domain, kinetic energy doesn't evolve that large of a change in anything, which goes back to the lowest linearity ratio as well. You can take a look at what happens with the change in latent heat at the surface. Shown here is kinetic energy, Bake, and mu. We see, especially with in all of them, we're seeing an increase in an annulus about the TC, where the more intense TC is stronger surface wind speeds, increase in the latent heat release from the surface. This signal is largest in the Bake simulation, which is consistent with the average value we found. Really won't go into this, but we also did with the Bake response function, made various perturbations to the atmosphere, looking at the vertical extent, so again, upper and lower levels, how close to the TC core sensitivities were, and also based on the inertial stability, how large, where are the sensitivities located and how do they evolve linearly. We found a clustering of certain partitions that evolved most linearly and actually helped a lot in our linearity ratio. We're still working on dissecting why exactly these certain cases evolved most linearly to change the TC. So, quick synopsis from research question 2. A big part of it was developing and applying this novel response function, Bake. It resulted in a higher linearity ratio, which we showed in one case study here, but is also the case across a number of other case studies I've performed. We believe this is because of the focusing of increasing Bake within the center of that response function domain. We also saw that this novel response function resulted in pretty consistent sensitivities to other traditional intensity metrics. We also developed some insights that how we're defining a response function needs to be considered, such as structure, if we really want to say how to intensify the TC and have a good relationship to the tangent linear model. Lastly, we again showed that partitioning the atmosphere results in different linearity ratios and different responses to TC intensity. The physical processes separating why this is the case is ongoing work. So to fully wrap up, through my dissertation, looked at two basic principles. One was Adjoint as a tool, what new applications and understandings can we gain from it. The second is looking at more physical processes that are occurring for TC intensification. From Adjoint as a tool, a big part of it was new insights about how response function for intensity need to be considered, such as structure. We also seeing how the TLM can shift the track and understanding why is that the most efficient way to increase TC intensity. Something not shown today was also looking at a more balanced response function. We also found that through partitioning the atmosphere, the linearity ratio is impacted, and that can have a benefit for when we're looking at adjoint case studies that are highly nonlinear. Lastly, we saw that response function definition influences the sensitivity gradients and thereby what processes are most important for development. On the physical response to adjoint perturbation side, we found optimal perturbations can be partitioned and a preference for where and to what the TC intensifies most readily to. We found the upper troposphere responds more linearly and robustly to perturbations, which highlights the importance of outflow dynamics, such as found in Rapin et al. 2011, which found the outflow driving development. We also found that with the same intended response functions, perturbing different parts of the atmosphere allows for different processes to drive development within the TCs. For more robust analysis and additional case studies is necessary to really prescribe significance to these perturbations. Which leads us nicely into our future work. Again, a large part is further analysis of these physical processes. An interest also is if we have enough of these case studies, can we create some type of composite or ensemble of case studies in order to find dominant signatures of sensitivity patterns or processes that are important for development. Also aspects of actual model initial conditions uncertainties and how those are related to our adjoint sensitivities in order to prescribe some actual significance of if we were to say do a targeted observation campaign and say deploy resources here, how do we know that where the adjoint says a model is most sensitive to develop also is very uncertain in the atmosphere. Lastly, working with a more sophisticated adjoint would be beneficial, such as the COAMPS adjoint at NRL, which is where I'll be starting this fall as a postdoctoral fellow. Lastly, to wrap up, acknowledgements. First, I'll have to thank my advisor, Michael, for his wonderful advice and bad puns over the many years. Very much so appreciated, and hard to say too much good things about that. Next, my committee, Chris Davis, Brett Hoover, Stephanie Henderson, and Greg Chipperley, all for your advice and support, helping develop my research and giving me advice throughout the years. I played professor for a semester, and Dan Beaumont and John Martin were instrumental in helping me develop that course. Also, Delta program, which I did my Ph.D. minor, and the affiliated instructors taught me a lot about teaching pedagogy. Can't forget my lab group members, past and present, for both helping me with research and also just making the time more enjoyable, as well as the high impact weather group for useful comments and discussion. Pete for all his technical magic that he does, as well as the office staff. As Michael mentioned about an hour ago, the AOS mentorship program was a dream of mine starting grad school, so very grateful to the many grad students who helped contribute to that, as well as my other AOS and non-AOS friends, Leslie, my family, and my dog, because she's great. With that, thank you for your time, and I'll take any questions.
Question?
All right.
So my question is, like, if you try this new response function bake with weak system or with tropical cyclone, and how this where is the difference comparing this response function with a strong tropical cyclone with weak cyclone? It responds the same way, just like.
Yeah, so far I've only looked, so the question was trying this response function on weaker storms. I've only looked at pretty strong vortexes as of now, but I think it would be interesting also to look at different case studies. I think it would have a similar response as far as increasing the linearity, but that's a good suggestion and definitely something. Looking at different phases in the life cycle of TC and evaluating it with adjoints. Juliet?
Great presentation, by the way. It's really neat. I was curious if you could comment on a study produced your work to study that relationship between maximum wind speeds and minimum sea level pressure and how those might be, comparing, I suppose, is good metrics for intensity and how they might be changing over time with respect to.
Yeah, so looking at the relationship between what we're seeing and different response functions and how they're related.
I think so.
So if we're increasing kinetic energy and vague, both wind-based metrics versus pressure, so I think something interesting, and because this is a ton of different cases, something interesting is it's not a one-to-one relationship that I found, where, for instance, perturbing inertially unstable regions, it's got a high linearity, it increases the relative vorticity, however, the sea level pressure also increases. So we're finding interesting results in here that this is not settled as far as how we're increasing if we're having a high linearity and increasing the vague, does that actually correspond to sea level pressure? So that's definitely an area of interest to continue to evaluate. Why is that not the case of increasing these wind-based metrics, also decreasing the minimum surface?
Thanks, yeah.
Nuo
Can you go to page 49?
49?
Yeah, so we can see that when you put in the perturbations in lower levels, the still kind of develop, the most of development happens in the upper levels, right?
Correct.
And what do you think that causes? It's just like the upward transport of energies and moisture from the lower levels to upper levels?
I think so, yeah. I mean, the outflow and the other TC and inflow, as air goes in, if it isn't evacuated out, the TC can't continue to develop, and you'll just get a pileup of mass, and the storm will eventually die out. So there has to be some type of increase in the outflow if we're trying to increase the inflow or the primary circulation about the core.
So does it mean that if you can directly, like you did for the upper perturbation, you don't go through any barriers of the transportation part? You just start to evacuate the upper level. But in the previous two cases, you have the barrier of going through all the friction or whatever, or loss of latent heating in the process to get to the upper level to do the same work. Does that make sense?
Yeah, yes, that makes sense. Was that a question or a statement? Yes. Yeah, so that's what we think we found. I forgot to mention this, but something that from this work and seeing how much the outflow is driving development when we're perturbing just the upper troposphere, creating an outflow-based intensity metric is something of interest to see if instead of saying I want to increase the low-level vorticity, what if we either increase the upper-level anticyclone or radial outward flow? If that's what we prescribe, how do we see the intensity as we typically define near the surface correspondingly intensify? Can we see the same development or different types of pathways to development by saying, well, the outflow is what's really driving the system?
And can you go 3 slides back in page 46 when you show the tangent linear model? My question then is, because we know if the model or the nonlinear perturbation follows the tangent linear model, then its linearity has to be 1. But you're saying that now we have the linearity ratio almost equal to 1, but they don't match. The perturbations don't match in tangent linear perturbation and nonlinear perturbation. This is say that I'm just kind of concerned with the using of linearity ratio to indicate it is actually linear.
Yeah, so this has been a discussion Michael and I have been having recent of comparing the tangent linear model, how best to incorporate a concept of structure within our response function and comparing these metrics. Lost my train of thought. So lots of different aspects here. One, we're not saying, when we're defining when we're saying we want to change mu at this time, we're not saying how, we're just saying on average. So it can do whatever it wants. And when we're comparing it, we're just comparing the average value within the response function domain. I know that the NRL COAMPS Adjoint group also does a correlation test to see how well correlated are the tangent linear model and the nonlinear model perturbations. However, that doesn't necessarily have a 1, even if that correlation is 1, if the magnitude is not the same, you can still get some issues. So thinking about additional ways to consider linearity is fresh in my mind, and if you have suggestions, we can probably take this as a later discussion.
Thank you very much for the presentation.
So Matt.
That's a pretty neat result that you have a sensitivity to the outflow. I guess probably Greg likes that pretty well. This idea, it may be relevant for future work. I don't know. What I've noticed in this community is for the past 10 years, there's 2 emerging points of view. One is the axis-symmetric, sort of 2-dimensional view. It's totally solely symmetric, and you can develop a hurricane that way. And that's the prevailing view. But this emergent one that a hurricane really is the sum total of all the individual convective elements, and that there's a lot of asymmetries, seems to hold a lot of merit also. I'm just wondering if maybe your methodology is ideal to investigate that question. Do zonal asymmetries really matter a lot, or do they not really matter much? You know, some discussions about secondary eye wall formation. When you look at the pictures, they're always in like one preferred quadrant or another quadrant. They're not symmetric. So I just wonder about those 2 points of view.
Yeah, I've been super curious about, you can find a sensitivity field, the difference between, pretty much nothing is perfectly axisymmetric. In this case, these sensitivities in this inner part is saying, make it more, the perturbation would be symmetric in this inner annulus, but not in this exterior sensitivity. However, if you project that on to the relative humidity, is that making the initial time relative humidity more axisymmetric, or vice versa as a way to perturb it. But yeah, somehow filtering out just axisymmetric versus asymmetric components acknowledgements could be an interesting way to partition the perturbations. John?
So what governs the choice of the size of the response domain? Because it seems to me in the limit of too small, you have some of the problems you talked about at the beginning of the talk, as well as the vorticity may increase in the wrong place. And if it's too big, you can't get the mass out of it, and so your averages don't mean anything. So how do you determine what to do?
Yeah, so not shown here is many experiments I've done to test that. So I've tried making it a little bit larger and a little bit smaller to see, does that have any systematic change on a combination of the linearity and the sensitivities, because both of those are important to see if I were to make it instead of 20 by 20, 40 by 40, or 10 by 10, that'd probably be too small. I haven't seen any significant differences as far as sensitivity goes, as I made a relatively small change about where it's currently defined. I think if you get too large, there's more chances. If you get too large, you get more, especially at higher, which 18 kilometers, while not a high resolution simulation, in Adjoint studies for this model integration is the highest I've seen done, published at least. So there are definitely nonlinear kind of convective elements that I see in the evolved fields. So the larger that response function domain gets, the more chance you have of that. And one convective element just having to initiate at that final response function time can then smear linearity and kind of some of the interpretations.
Yeah, I guess what motivated is your experiment where you had inertially unstable environment surrounding your domain. And one of the ways I was thinking about it, and probably incorrectly, is that makes it easier to get the mass out of your domain. So you can have, if it's the wrong size, or if it's sensitive to size, you could either have a result that says the pressure in the box on average goes down, or the pressure in the box on average goes up, because you just moved it to another shelf in your box because it's too big. So that's why I was wondering about the size.
Yeah.
So the mass has to leave that column.
Which the inertial stability within this within this model domain is highly dependent on the TC structure and its strong cyclonic circulation. Yeah.
Thanks.
Any other questions?
So one. So can I ask, the vague function seems to be like a direct function of the vorticity that's in your chosen response function box, right?
Yes.
So would we expect, or why would we expect there to be any difference in the behavior of this response function as opposed to just the vorticity in that same box?
That's a good question. I have done simulations with also comparing vorticity. Sensitivities, again, are pretty consistent, not the same. I think that with this response function, there's a little bit more of an element of structure associated with it, and where we're telling it implicitly to increase the vague, which vorticity, similar to sea level pressure, doesn't necessarily have that same kind of structure element to it. So I think that could be a benefit. But I haven't done vorticity as many simulations comparing vague to vorticity as a response function by itself.
Just to Brad's point, is it possible that when we define the vorticity as the response function, we actually use the circulation definition?
I think that's what we typically use is.
And so I assume that when creating the vague, you have to invert the vorticity,
Correct.
and that kind of creates a balanced adjoint forcing. So the vorticity response function might not have this balanced part in it, but the vague might have.
Yes. Yeah. So I didn't show it here, but an interesting unintended consequence of a vague response function is because we're inverting the winds from the vorticity, we're getting just the rotational component of the flow, more or less filtering out the divergent component. And so when we initiate the adjoint, there's a known issue of high frequency waves. That's essentially a gravity wave adjustment. I should have had an extra slide on. But we don't see that we see that signal significantly smaller within the Bache response function compared to kinetic energy, and especially the surface pressure response function. We also see that kind of non-physical high-frequency wave decay the quickest within Bache, which goes to the fact that it's a more balanced, not perfectly balanced response function.
Okay, well, let's thank our speaker again.